Let's be honest, physics problem books can be pretty intimidating, right? Especially one like I.E. Erdov's Problems in General Physics. Well, today, we're going to tackle one of the classic challenges from that very book. We're going to take a tough gravitation problem and break it down step by step until it's totally clear. So what's our game plan? First, we'll get a solid grip on what the problem is actually asking. Then, we'll brush up on the key concepts of work and potential energy. After that, we'll lay out our plan of attack using integration, do the calculation, get our final answer, and then we'll wrap it all up with the most important takeaways and some common traps to avoid. It's a clear roadmap from start to finish. All right, let's get right into it. First things first, what exactly is the problem we're trying to solve? Okay, so here it is, straight from the book, problem 1.213. We've got a small particle, mass m, and it's being moved from the very center of the base of a hemisphere, mass m, all the way out to infinity. The big question is, what's the work done by gravity during that trip? So let's get a picture in our heads. Imagine a solid hemisphere, like half a bowling ball, sitting flat on a table. Right in the dead center of that flat circle, we have our tiny particle. Now we're going to move that particle away from the hemisphere. And we're not just moving it across the room, we're moving it infinitely far away. Our job is to figure out how much work the hemisphere's own gravity did on that particle over the entire journey. Now, before we start crunching numbers, we have to make sure we're using the right tools from our physics toolkit. This problem isn't about brute force. It's about understanding a really elegant relationship between work and energy. And here it is. The single most important concept for solving this. Gravity is what we call a conservative force. Now that's just a fancy way of saying that the work gravity doesn't care about the specific path you take. It only cares about the starting point and the ending point. That is huge. It means we can calculate the work, A, as the negative change in potential energy. This little equation is the key that unlocks the entire problem. Now here's where physics gives us a really nice gift. By convention, we just define the gravitational potential energy between two objects to be zero when they are infinitely far apart. And since our particle's final destination is infinity, well, we already know its final potential energy. U final is zero. Boom. Half of our equation is already figured out.
And this is that aha moment. This is why we use this concept. If our work A is negative of U final minus U initial, and we know U final is just zero, the whole equation simplifies beautifully. It becomes A equals negative of 0 minus U initial, which is just A equals U initial. Amazing! That whole complicated problem of calculating work over an infinite path just boiled down to a single, much simpler task. All we have to do is find the potential energy of the particle right at the very beginning.
So our mission is clear. Calculate the initial potential energy. But how in the world do you do that for a big, spread-out object like a hemisphere? Let's build our plan of attack. This is the real heart of the challenge, isn't it? We can't just use that simple potential energy formula you learned for two-point masses, because the hemisphere's mass is all over the place. Every little speck of the hemisphere is a different distance away from our particle, and each one contributes its own little bit to the total potential energy. So how do we handle that? Well, we bring in the big guns, calculus. But don't worry, the idea behind it is actually super simple. First, we're going to mentally chop up the hemisphere into a bazillion tiny little pieces, each with a mass we'll call dm. Second, we'll figure out the potential energy from just one of those tiny pieces. And third, we'll use an integral to add up all those tiny contributions together. That's it. Okay, the strategy is in place. Time to roll up our sleeves and execute the plan. This is where the math comes in, but we're going to walk through it logically, step by step. First things first, and this is a crucial choice, our coordinate system. I'll tell you right now, trying to do this with regular x, y, and z coordinates would be an absolute nightmare. Since we've got a piece of a sphere, the natural, obvious choice is to use spherical coordinates, r, theta, and phi. It just makes describing the shape so much easier. So here's where the magic of calculus comes in. Even though the whole hemisphere isn't a point, any one of those teeny tiny infinitesimal chunks of it, dm, is basically a point. So for that one tiny piece, we can use the familiar potential energy formula. We call its tiny contribution du, and it's just negative g times the particle's mass m times that tiny mass dm, all divided by its distance r. Okay, but what is this little dm thing really? Well, we know that mass is just density, which we call rho times volume. So our tiny mass dm is just rho times a tiny bit of volume dv.
In spherical coordinates, that tiny volume element has a standard formula. It looks a little wild, r squared, sine of theta, dr, d theta, d phi, but it's just the recipe for a tiny brick-like shape in a spherical system.
And here's the whole shebang, how we put all those pieces together. We're going to sum up, or integrate, the potential from every single one of those tiny masses. So let's look at the limits, because they're super important. For the radius, r, we go from the center at 0 out to the edge at r. For the angle that sweeps around the base, phi, we go a full circle, 0 to 2 pi. And for the angle that comes down from the top, theta, we only go from the very top at 0 down to the equator at pi over 2. These limits are what define our shape as a hemisphere and not a full sphere.
Now, we're not going to grind through all the calculus on screen, but the process is basically to solve the integral for each variable, one by one. After you do all that, the last step is to replace the density term, rho, with what it actually is, the total mass, m of the hemisphere, divided by its total volume, which is 2/3 pi r cubed.
We have officially done the heavy lifting. We've gone through the calculus and found the initial potential energy. So now, let's take that result and finally answer the original question. Okay, let's bring it all back home. Remember our big breakthrough from the beginning? That whole complicated work problem just simplified down to finding the initial potential energy? So, the work, A, is simply equal to U initial. And there it is. After all that work, the integration and the substitution, we get our final answer. The work done by the gravitational force is -3/2 times gmm over r. But hold on, what's with that negative sign? It's not just a math artifact. It's telling us something really important about the physics. Gravity is an attractive force, right? It's trying to pull the particle toward the hemisphere, but we're moving the particle away from it. The force and the displacement are in opposite directions. Whenever that happens, we say the force does negative work. So that negative sign makes perfect physical sense. Woo! You know, solving a problem like that is a fantastic workout for your physics brain. So let's just quickly recap the big lessons here, and maybe even more importantly, look at some of the common traps people fall into. So what are the big ideas to remember? First, this super useful shortcut. For move to infinity problems, the work done by gravity just equals the initial potential energy. Second, to handle any weirdly shaped object, you find the total potential by integrating, by adding up all the little pieces. And third, for the love of physics, please choose a coordinate system that matches the shape of your problem. It'll save you so much grief. And here are a few landmines to watch out for. First, you absolutely cannot treat the hemisphere as a single point mass, located at its center of mass for this calculation. It just doesn't work for potential. Second, be so careful with your integration limits. If you used 0 to pi for theta, you'd get the answer for a full sphere. Third, always double-check your signs in the work-energy relationship. And finally, notice the problem says the particle starts at the center of the base, which is different from the hemisphere center of mass. So there you have it. We took a beast of a problem and we broke it down piece by piece. But the real test of understanding is being able to apply these ideas yourself. So I'll leave you with a little challenge. Using the exact same strategy, how would the answer change if the particle started not at the center of the base, but at the very top of the hemisphere's dome? Give it some thought. Thanks for joining me for this explainer.